Welcome to this video. In this video, we will be discussing about the inverse kinematics of a robotic manipulator. In this video, the following topics are being covered. We will first discuss about what an inverse kinematics is, and we will discuss about the joint space and task space, and we will also discuss briefly about dexterous workspace and reachable workspace and general properties of solutions of inverse kinematics, and finally we will do a problem uh, related to inverse kinematics of a 3 degree of freedom robotic manipulator. So earlier we already studied the direct kinematics, in which we used DH criteria to assign coordinate frames and finding successive transformation between adjacent coordinate frames, and finally we were able to get a transformation matrix from the end effector to the base. The transformation matrix which we obtained was of the following form. It contained a rotation matrix R and a row matrix P, where R denoted the orientation of the tool with respect to the base frame and P denoted the position of the tool with respect to base frame. Then, so in direct kinematics, we were simply able to find the position and orientation of the tool when Q1, Q2, Q3. That means when the joint parameters were already given. So when the joint parameters were already given, and when we substituted those parameters into the transformation matrix, we got the resultant orientation and position of the tool or end effect. But what if we need the values of joint variables if the position and orientation is given already? For this, we need inverse kinematics, or this problem exactly is called inverse kinematics. So before moving into inverse kinematics, first we will discuss what is joint space and task space. So for an n-axis robotic manipulator, we all know that there will be n joint variables. Okay. This set of joint variables, which is basically an n by 1 vector, belongs to the set Rn, and this vector space is called joint space. So the joint space means the vector which represents the joint variables is belonging to that particular vector space, and that vector space is called joint space. And the size of that is basically an n by 1 vector. And similarly, there is also something we call as task space. The position of the tool can be referred to as configuration of the tool, and the tool configuration parameters, which is R and P, can be associated with a subset W of R6, and this vector space is called task space or configuration space or Cartesian space. So basically, the rotation, we found out the rotation matrix and the position coordinates, right? The position coordinates contains 3 components, whereas the rotation matrix is a 3 by 3 matrix and it contains 9 components. But we all know that the orientation of the tool can be represented using 3 variables only, which is yaw, pitch, and roll angles. And that three variables for orientation and 3 variables for position will give you a 6 by 1 vector, and that vector actually belongs to R6, which is called the task space or configuration space or Cartesian space. Okay, so these are basically task space and joint space. Now we will see that So let this be the joint space and let this be the task space. So from joint space to task space, if you want to convert the parameters from joint space, so if you are given the values of joint variables, that is the parameters in joint space, then you can convert it into task space using direct kinematics. Similarly, if you are given the parameters of the task space, which is a 6 by 1 vector, and you want to find the components of the joint space, which is the each joint variables. It could be the revolute angles of each joints, or it could be the length of the each joints if it is space, it is a prismatic joint. So if you want that those parameters, then you will need inverse kinematics. So why do we need inverse kinematics? So robots basically move by adjusting their joint. We are in each joint we might be connecting some motors or some hydraulic drives or something, and we need to actually control those joints in order to make the robot move to a particular position or orientation. So uh, but we as a human being are more uh, comfortable with expressing the position and orientation in terms of uh, three yaw, pitch, roll, and three coordinates of the position. So basically we are more comfortable in expressing every position and orientation in task space only. But for controlling robot, we need that individual values for joint variables. So for that, we need inverse kinematics. And inverse kinematics basically calculates the specific joint angles needed to achieve the desired position and orientation required by the application. And position and orientation can be generally called as pose. So the term pose means position and orientation. Now, without inverse kinematics, let's say there was nothing as inverse kinematics, then it would have been very difficult to adjust the robot automatically. Especially if you are programming it using some microcontrollers, it would have been very difficult. We had to manually find out every joint values for every corresponding value, position and orientation. That would have been very difficult, but rather than that, we can simply solve the inverse kinematics problem, and we can get the values rather than doing it manually and finding out each specific values of joint variables. So that's why we need inverse kinematics. This is particularly useful when we are using robots to grasp object from a specific location, and if you want it to place that object in a specific position with a specific orientation, or when you are dealing with uneven surfaces, or when you have some obstacles, we need that inverse kinematics uh, algorithm uh, to get the corresponding values of joint parameters every in real time. Also, inverse kinematics plays a vital role in planning robot paths and motion trajectories. It ensures desired positions while avoiding collisions and obeying joint limitations. So that's why we need to solve the inverse kinematics problem, and that's why we are very interested in studying inverse kinematics. Okay, now we will define, uh, we have already studied what a workspace is, and we will compare two terminologies, that is called dexterous workspace and reachable workspace. So we know that, what do you mean by workspace? Workspace means the volume of or the space in which the where which the end effector or tool can reach. That is what we call as workspace. So why do we why are we caring about workspace? Because it is very important if we are solving inverse kinematic problems. Because if you are asking if you are giving a position and orientation which is outside the workspace, and if you are telling the computer to solve uh, find the corresponding joint variables for that particular position and orientation, it it is not possible if that given position and orientation is outside the workspace. So that's why we care about studying workspace. So for every values of position and orientation, we might not get a set of values for joint variables. This depend on the workspace of the robot. So the two crucial terms that define the capabilities of a robot's arm are reachable workspace and dexterous workspace. So first let's see what reachable workspace is. So the reachable workspace is the maximum volume of the robot's end effector can access. The so it is the maximum volume that a robot's end effector can access. That is what we call reachable workspace. So this space is actually influenced by several factors. First one is robot's arm length and joint range. So every robot has a particular length, every link has a particular length, and the reachable workspace is limited by the arm's length and joint range. What do you mean by joint range? There is a particular range in which the joint can move. That is what we call joint range. And the next one is obstacles. If there are obstacles in between the robot, then that areas also will not be accessible by the robotic arm. So that also determines the reachable workspace. Similarly, the third one is joint constraints. So every joint will have some kind of constraints. Maybe it can't take some range of angles or something like that. So that also affects the reachable workspace. So we have studied reachable workspace. Then what is dexterous workspace? That is what we want to see. So the dexterous workspace is the area where the robot can not only reach but also manipulate objects with full dexterity. Okay, it can not only reach but it can also manipulate objects with full dexterity. What does it mean? That it means that the robot can not only reach that space, but also it can take any orientation and any position, it can access its full degrees of freedom at that space. That is what we call dexterous workspace. So one example is that if we are using a robotic arm to open a door by twisting a doorknob, then that robotic arm needs to have a degree of freedom which enables it to orient it in such a way that the doorknob is twisted. So that kind of manipulation should be needed at that position. On that is what we call dexterous workspace. But just imagine if it is only barely reaching that doorknob without able to do anything else. That then that doorknob will be within reachable workspace, but it won't be within dexterous workspace. That is what it means. So let's compare the reachable workspace and dexterous workspace. So dexterous workspace is basically a subset of the reachable workspace. So the reachable workspace will be the larger volume and the dexterous workspace will be very smaller than that. Okay. And reachable workspace is about access, means whether it can reach or not, while dexterous workspace is about manipulation. It means that in that space the robot should be able to manipulate in any orientation. In reachable workspace, the end effector can reach a point in at least one orientation. Okay, so that means it just has to barely reach that point. Then it will be under reachable workspace. It it only need at least one orientation. for it to reach there. That is what we call reachable. That area, that space will be under reachable workspace. But in dexterous workspace, the end effector should not only reach but also should be able to orient it in any direction. So that is, that space will be under dexterous workspace. So basically, reachable workspace will be a big area, the maximum area where it can reach, while the dexterous workspace will be area where it can manipulate freely. So these are basically the differences between reachable workspace and dexterous workspace. Next, we will be looking at the solution of inverse kinematics. Inverse kinematics is complex because the solution is to be found for nonlinear simultaneous equation involving transcendental harmonic and cosine functions. Okay, the basically while solving, you will see that while writing down the problem for inverse kinematics, what we are getting is basically some nonlinear simultaneous equation. It contains sine function, cosine function, and all kind of function, and therefore it is very difficult to solve those kind of equations. If it were simple linear algebraic equation, it would have been very simple. We just needed to calculate using our pen and paper, or we could have using some matrix methods. But this, when it comes to nonlinear equations, there is no such fixed method to solve those kind of equation. That's why it becomes very complex. So also multiple solution or non-existence of solution. So either there can exist multiple solution, or there is also a possibility that no solution could exist. These conditions are all possible in inverse kinematics. There are two approaches for finding solution of inverse kinematic problems. One is analytical methods, then is numerical methods. So analytical method is basically we are just solving equation by manipulating it here and there, and we will get some kind of expression. So we will see about that. So in using analytical methods, we will make use of the equation, make use of the structure of the equation, and we will try to find a solution for the equation by doing it in hand. And by doing that, we will get a closed form expression for the solution. Okay, we will get a complete solution. Some is equal, x is equal to this one, y is equal to this one, that kind of some kind of expression we will get for analytical, when we are solving it in analytical methods. And doing finding the solution using analytical methods are considerably faster than numerical approximation methods, and they can also be used to identify multiple solutions. Earlier we mentioned that in inverse kinematic problem multiple solution could exist, and by solving the inverse kinematic problems using analytical methods, we can we can identify multiple solutions. But the main drawback of this method is that this is robot dependent. Okay, it depends on each robot, each class of robots actually. So for each class of robots we need to do it manually, find out the expression, everything, and in some cases that process may be very difficult, and it may not be feasible to do that, and it might not be possible also. So that is the main drawback of this kind of methods. The next method, which is also a very popular method in when especially when we use computers or some kind of processors for finding out the inverse kinematic solution for inverse kinematics, they are using numerical methods. So numerical methods such as the Newton-Raphson's method can be used to find the uh, the joint coordinates when the coordinates in task space is given. So if the position and orientation is already given, we can find the values, corresponding values in terms of joint variables, and we can make use of some kind of optimization techniques. Basically, numerical methods are all kind of optimization problems where we will define some kind of optimization, some kind of cost function, and we will be seeking to reduce that in each successive iterations, and that depends on the initial guess also. So if the initial guess is actually close to the actual solution, so for example there are 3 degrees of freedom and there are 3 joint variables, theta 1, theta 2 and theta 3, and we are guessing theta 1 something, theta 2 something, theta 3 something, something like that. If the initial guess is close to the actual solution, the iteration may converge rapidly, but if it is not, it may take a lot of time also. So the main advantage of a numerical approach is that it is robot independent. That means for every class of robot, we can use the same technique. It does not change depending on different class of robots. But the main drawback of this method is that this is very slow and it only provides a single and approximate solution. Okay, it will not give you multiple solutions that might exist, and for each guess, okay, if there exists a multiple solution, for we have to do the iteration for different initial guesses, only then we will get some kind of multiple solution, but in one go we will not be able to get any multiple solutions. Okay, and also the solution will not be exact, it will be approximate. For example, if the value of theta event should have been 45 degrees, then you might get 44.98 something in approximate value. It finally depends on the number of iterations that you are doing. The next we have looked at what are the different methods for solving inverse kinematic problem, and next we will be looking at the general properties of the solution of inverse kinematics. So although we use different methodologies and we might get different solutions for different kind of robot, so but a general property can be seen while observing the solution of inverse kinematics. The explicit solution to the inverse kinematic problem depend upon the robot or the class of robots being investigated. But there are certain characteristics of solution that hold in general. They are existence of solution and uniqueness of solution. So the properties that we are going to focus are existence and uniqueness of the solutions. First, we will look at the existence of the solution. If the desired tooltip position P is outside its work envelope, then no solution can exist. So we have already mentioned it already. That is, if it is outside the workspace, if it is outside the work envelope, then no solution can exist. Whatever the position and orientation that you give to the computer, you will not get a solution that is acceptable. Then even if P is within the work envelope, there may be certain tool orientation which are not realizable without violating one or more joint variable limits. So basically these are practical devices. So every joint may have some kind of limitations, and even the position orientation that we are giving is within the work envelope, it might not be able to realize that, because if that violates the joint variable limits, it might not be able to realize that. We won't be able to get any kind of solution out of that. If the robot has fewer than 3 degrees of freedom to orient the tool, then whole classes of orientations are unrealizable. So we have already seen that for orienting a robot in any direction, we need 3 degrees of freedom for that only. It should independently rotate in about three different axes. So if there are no degree, if there are less than 3 degrees of freedom, then the whole class of orientation will not be realizable. Then also in that case also we won't get a solution for every kind of orientations. That is what we are meaning. So there also the existence of solution is not possible. Now let's look at the arm equation. So the arm equation basically consists of the rotation matrix and the position of the tooltip. So in the rotation matrix there are 9 parameters. Basically there are those are expressions, right? R11, R22, everything are expressions in terms of joint variables, sin theta 1, cos theta 1, a complicated expressions we will get depending on the degrees of freedom of the robot. And P also is some kind of expression which if we substitute the joint variables into it, we will get the corresponding position and the orientation. This is the arm equation of the robot, which we usually get using by solving the direct kinematics. So if you look at this arm equation, this constitutes a system of 12 simultaneous nonlinear algebraic equation. Okay, that is, we can see that it is basically, let me write the, so see the, this will be some kind of expression, okay, depending on, let's say s1 2 3, like sin theta 1 plus theta 2 plus theta 3, something like that. Each one of this will be some kind of expression. And if you are giving a, if you are already giving a position and orientation uh, to that, we can get the corresponding r and p. We will know these values, right? We will know these values. This will be 0 1, and by comparing these two matrices we can basically get 9 equations from the rotation matrix itself. This is equal to some value, this is equal to some value, this is equal to some value, and similarly we will get 9 equations. Similarly 9 plus for the 3 components of the position coordinates we will get 3 additional equations. So basically we are getting 12 simultaneous non-linear equations. Okay, but the number of how many unknowns we have for, if the robot is a 3 degree of freedom robot, the number of unknowns will be 3. If it is 3 degree of freedom, number of unknowns will be 3. If it is 6 degree of freedom robot, 6 degree of freedom robot, the number of unknown will be 6. Similarly, if it is 7 degrees of freedom robot, then the number of unknowns will be 7. Okay, so the number of unknowns indicates the number of components of the q vector, which is q is basically the vector of joint variables q1 q2 q3 q4 up to qn. And we have, so on one side we have 12 simultaneous equations and we have n number of unknowns. Let's see whether using, by analyzing that, in what condition we will get the solution. The, okay, the 3 columns, you have already seen that the rotation matrix, we have already studied that rotation matrix is basically an the 3 columns, the column 1, column, these 3 columns are basically orthonormal sets. What do you mean by orthonormal sets? That is, this, each of these columns are mutually perpendicular. Okay, let's say, let name is it as r1, r2, r3. So r1 is perpendicular to r2, r2 is perpendicular to r3, and r3 is perpendicular to r1. R3 is perpendicular to r1. So because this is an orthonormal set, we get 3 constraints. Okay, uh, think about it. We have 12 simultaneous equations, but the thing is, these 12 simultaneous equations are not independent equations. Okay, some equations are dependent between each other. So we are actually trying to find how many independent equations are there. So while analyzing the rotation matrix, we can see that because these three columns are mutually perpendicular to each other, there are three constraints included there. Similarly, we can see that each of this column is actually having length 1. So basically the norm of R1 is actually 1 and norm of R2 is similarly 1. This is R2 is equal to 1, and similarly R3 is equal, norm R3 is also equal to 1. So basically here also 3 additional constraints are being introduced. 3. So 3 plus 3 we get 6 additional constraints. Okay, 3 constraints here and 3 constraints here. We will get 6 additional constraints. We have 12 equations. So 12 minus 6, we will get 6 independent equations. Okay, so at the end of the day, we are left with 6 independent equations and n degree of freedom in unknown components. Okay, now what does n indicates? Okay, n indicates obviously the components of the joint parameter, joint variables. So joint variable will contain n number of parameters, q1, q2, etc., q3. This is the number of joint q3, not qn. And this is the this n indicates the number of components of the vector of joint variables. Also, this n also indicates the degrees of freedom of the robot. Okay. Okay. So n indicates the degree of freedom of the robot. So n should be at least equal to 6. Okay. N should be at least equal to 6 for the inverse kinematics to have a general solution. What does it mean? So we know that a rigid body in a three-dimensional space needs at least 6 degrees of freedom to take any position and any orientation. Okay, any position and for taking any position and any orientation, it needs at least 6 degrees of freedom. So similarly, if the robot should have 6 degrees of freedom for it to have a general solution for inverse kinematics. That is, if you are giving the position and orientation within the work envelope, for it to give the values for joint parameters, the degrees of freedom should at least have 6 degrees of freedom. The robot should have 6 degrees of freedom. Only then we can find values of q. That is what we mean by the general solution. Okay. So n should be greater than or equal to 6. Okay. The lower bound, okay, the lower bound on the number of axes is necessary but not sufficient condition. That is, it is a necessary condition. Okay, without it, without n should at least be equal to 6 for it should for the inverse kinematics to have a general solution. Okay, this is necessary condition, but this is not sufficient. Okay, this condition must be there, but this is not but having this condition will not necessarily uh, give you necessarily tell you that the solution will exist. Okay, so my robot is having 6 degrees of freedom, but still I won't be able to say it in confidence that I will have a solution for the inverse kinematics, general solution. This is just a necessary condition, not sufficient. Now this is the discussion on existence of solution, and the existence will depend on different robots, and that has to be observed individually, but this is a general outlook. on the existence of solution. Next, we will discuss about the uniqueness of the solution. So even if the solution to the inverse kinematics problem exists, they might not be unique. Okay, let's say it once more. Even if the solution to the inverse kinematics problem exists, they might not be unique. Okay, multiple solution could exist. So what are the cases where multiple solution exist? So let's say the degrees of freedom of our robot in is greater than 6. Infinitely many solutions can exist for the inverse kinematic problem. So these kind of robots are basically called kinematically redundant robot. So they have more degrees of freedom than are necessary to establish arbitrary tool configuration. So basically ideally we only need 6 degrees of freedom to get into any position and any orientation. But the additional, it has more degrees of freedom than that. Okay, that is why we call them kinematically redundant robots. So these extra degrees of freedom add flexibility to the robotic manipulator. So let's look at an example. Okay, so let's say this is considered, this is a planar robot. So we can see that in this case, uh, uh, in case of planar situation, we only need 3 degrees of freedom, but in this robot there are 4 degrees of freedoms. Okay, so 4 degrees of freedom where here there is a, this is one joint, this is second one, this is third one, and this is fourth one. 4 degrees of freedom are there. So in case of planar robot, it is not necessary to have a 4th degree of freedom robot, but it still has that. So because it has a additional degrees of freedom, it is able to avoid the obstacle and get into the container. Okay, it is getting around the around this walls, and it is going inside because this has an additional degree of freedom. So for redundant robots, the properties such as obstacle avoidance and multiple solutions, all those are possible. Then let's look at another example. So in this example, this is also a planar robot, and here also there are more degrees of freedom than necessary. So this is an example of a robot having multiple solutions. So this robotic manipulator is needed to reach that particular point P. So this is one orientation. This is one configuration which it can take to reach that position. And let's see another solution. So this is also another way in which it can reach that position. So it emphasizes that for the same problem, for the same position and orientation, we can have different values of joint coordinates, different solution for the same problem. So in this demonstrate that the inverse kinematic problem is actually not unique. Okay, next we will discuss a problem on inverse kinematics of 3 degree of freedom robotic manipulator, and this is a simple problem which could be solved analytically. We will not be using numerical methods. So the problem is that we have to determine the joint angles theta 1, theta 2 and theta 3 of a 3-axis robot if the origin of coordinate frame 3 is located at points 707, 1.707 and 0, and the orientation of the uh, third coordinate frame with respect to the first base coordinate frame is given by the rotation matrix, and also the arm equation which relates the third coordinate frame to the base coordinate frame is also given. So we are given with the rotation matrix, the position coordinates, everything. We just need to find the uh, theta 1, find the theta 1, theta 2, theta 3. That is, we have to find the joint variables of this particular given position and orientation. And the link length is also given, L1 is equal to 1 and L2 is equal to 2. Now we will start solving this problem. So if you are considering the, let's first look at the uh, let's look at the if you analyze the arm equation, we can get that the position x is equal to is given by L1 C1 plus L2 C2, where y is equal to L1 S1 plus L2 S12. So we get, and Z is basically 0. Assume that X, Y, Z is the position of the tooltip. So actually the values of X, Y, Z is already given, 0.707, 1.707 and 0. But let it be like this. Okay. We will assume it to be X, Y, Z for now, just for solving the equation. After that, we will substitute the equation. So let's do this operation. That is x square plus y square is equal to, when we will do this operation, we will get something like this. So basically x square is what? X square is L1 square cos square theta 1 plus L2 square cos square theta 1 plus theta 2. This is x square. And what is y square? Y square is equal to L1 square sine square theta 1 plus L2 square sine square theta 1 plus theta 2. Basically, we are basically adding both these things. So if you are adding this, you will get x square plus y square is equal to, we can take L1 square as common, and L1 square into cos square theta 1 plus sine square theta 1 plus, okay, there is an additional term also, I forgot to write it. This is plus 2 L1 L2 cos theta 1 into cos theta 1 plus theta 2. Similarly, here also plus 2 L1 L2 sine theta 1 into sine theta 1 plus theta 2. These are the expressions, and we will now combine it to make it simple. So now it will be L2 square into cos square theta 1 plus theta 2 plus sine square theta 1 plus theta 2 plus, here there is 2 L1 L2, we will take common, we will take it common, 2 L1 L2 into, this is basically cos theta 1 plus theta 2 sin theta 1 plus theta 2, basically cos A cos B plus sin A sin B. So we can simplify it as cos theta 1 plus theta 2 minus theta 1, and this will give us, this is equal to 1, this is equal to 1, and this will give us L1 square plus L2 square plus 2 L1 L2 cos cos theta 2. Okay, now from this equation we can get the value of cos theta 2. and the cos theta 2 must lie between -1 and +1. Now using that expression, we will actually substitute the values for x, y, L1, L2, etc., and we will get a value for cos theta 2 as 0.707, and theta 2 will be equal to 45 degrees. Now that we have found theta 2, we have to find theta 1. Now again, using the arm equation, L1 C1 plus x is equal to L1 C1 plus L2 C1 C12, and we can expand C12 as cos theta 1 plus theta 2, and we can rearrange it in such a way that we can write it as x is equal to C1 into L1 plus L2 C2 minus S1 into L2 S2. Basically, we are expanding this one. Cos theta 1 plus theta 2, we are expanding it. We are multiplying it inside. This is basically cos theta 1, cos theta 2 minus sin theta 1, sin theta 2. That's why we are writing it as C1, C2 minus S1, S2. And we have rearranged it in such a way that this into C1 and this into S1. So we will substitute for this as K1 and this as K2, and we will get an expression like K1 C1 minus K2 S2. Similarly, for Y also we can do the same operation where we will get an expression like this: K1 S1 plus K2 S2. Now we will define an R which is equal to root of K1 square plus K2 square and phi tan inverse K2 by K1, and where K sin phi and cos phi is given by K2 by R and K1 by R respectively. And we will modify the equation for x as x by R is equal to K1 by R C1 minus K2 by R S1. Similarly for Y also, Y by R is equal to K1 by R S1 plus K2 by R C1. Now why we are doing this is because we are trying to manipulate it in such a way that we can get this expression finally. So we are actually doing that, and we because that's why we have defined that cos phi is equal to K1 by R and sin phi is equal to K2 by R, something like that. So we will be getting this kind of expression, and we will write it in this form: cos theta 1 plus phi. Similarly, y by R will be equal to sin theta 1 plus phi. Now using these values, we can get the expression for theta 1 plus phi, which will be equal to uh, tan inverse y by R by x by R. Now from this we can get the value of theta 1. This will be the expression. Okay. Now all we have to do is substitute the values, and after substituting the values, we will get an expression like this for R. R will be 1.847, x by R will be this much, y by R will be this much, and solving these equations we will get the value of theta 1 as 45 degrees. So now we have got theta 1 and theta 2. So if you look at the transformation matrix, in that we can see that S123, that is sin theta 1 plus theta 2 plus theta 3 was equal to 0.866, and similarly cos theta 1 plus theta 2 plus theta 3 was equal to 0.5. So using that knowledge, we will find the values of theta 1 plus theta 2 plus theta 3, and it is obtained as 60 degrees. And if you substitute the values of theta 1 and theta 2 into this expression, we will get theta 3 is equal to minus 30 degrees. Thus, finally, now we have got every values: theta 1 plus theta 1, theta 2, and theta 3, everything. So this is how you solve an inverse kinematics problem. And so you can see that we have used some manipulations to solve it efficiently. This is simply because we knew this robot beforehand, and we have tried different ways, and we got this kind of methodology. But this is not true for every kind of robots. If you are getting a robot of different configuration, the solution, the approach to the solution might be very different. But for a 3 degree of freedom robot, having with all joints being revolute, we can actually safely use this approach to solve the equation, solve the inverse kinematic problems. So that is basically it in terms of inverse kinematics, and we will further discuss tool configuration, vector, Jacobians, etc. in further video. Thank you.